Hi, my name is Meera Hahn, and I will be presenting our paper, Transformer-Based Localization from Embodied Dialog with Large-Scale Pre-Training. In this work, we focus on localization via embodied dialogue task, where there are two agents, able to communicate only through natural language dialogue, with the goal of one agent localizing the other on a map. To contextualize this task, imagine going to a friend's house for the first time and you want to pick something up. They're not home, but they told you to find your item in the kitchen. Not sure where you are and not sure where the kitchen is, you call your friend to figure out how to get there. They don't know where you are, so you start by describing your surroundings. I am in a hallway facing brown double doors, and there's an abstract painting on my right. They may ask you to move or look around. If you go down the hallway and take a left, do you see the kitchen? So you start navigating in response to their questions. After a few or more rounds of back and forth, your friend has determined your location and can give you more precise directions. Going forward, we refer to the lost agent who is navigating as the observer and the agent with the map as the locator. The Where Are You dataset contains a little over 6,000 episodes of humans performing this exact localization task, providing us with an annotated training and testing set for the task. However, while the dialogue in this dataset is descriptive and diverse, the number of episodes is still quite small, and in this work we will show how to use pre-training data from the web to prevent overfitting to the training set and encourage the model to learn language grounding. In addition to the small number of episodes, the WAY dataset is situated over the Matterport 3D environments. This photorealistic 3D indoor environment dataset is also limited in terms of size and has only 90 environments in total. As the LED task requires generalization to new environments at test time, this size limitation creates a trend for the model to overfit to training environments. Again, we show this bias can be overcome via pre-training. The specifications for the LED task are as follows. The multimodal input for this task is a partial or complete dialogue between the locator and the observer and a map of the environment. This is input to a localization model. The model solves the state estimation problem of localizing the observer. And the prediction can be evaluated using localization error via Euclidean or geodesic distance. A key design choice for this task is about the format of the map that is given as input to the model. While prior work has addressed this task using a 2D image constructed from taking a top-down projection of the environment, we do not. This choice was qualified by the straightforward comparison to human performance, however, we are not restricted to this choice. Instead, we propose to use the RGB panoramic nodes of the Matterport 3D dataset as the input map representation, and we will show this leads to higher model performance. The RGB panoramic nodes of the MP3D environments compose a navigation graph for the scene. This is the same navigation graph used by the observer when it moves through their environment. Using this format therefore allows our model to know information about the structural layout of the environment as well as what areas are navigable. With this map representation, we can imagine the model encoding information about the visual features of the nodes as well as pose information via the edges. We propose to evaluate the localization error of our model using geodesic distance instead of Euclidean distance as used in prior work. Geodesic distance is more meaningful than Euclidean distance for determining error across rooms and across floors in a multi-story environments. The navigation graph representation allows us to easily calculate error in terms of geodesic distance. We propose a few simplistic baseline to test how simple language and visual encoders perform over the RGB panoramic nodes. In these baselines, edge information is discarded and the input to the model is just the visual panoramic node features and the dialogue. The model outputs either an alignment score or a probability bit distribution over the nodes, from which it can predict a node as the final location of the observer. To discern the precision of the tested models, we test over the weigh dataset splits, and report a binary success metric that places a threshold K on the localization error. Accuracy at 0 meters indicates the correct node was predicted. Accuracy at k meters indicates that the node was predicted within k meters of the true node. These results are shown here over the val-unseen split for the baseline models. In the baseline models, the locator and observer messages are encoded using a single layer bidirectional LSTM. In the first model, called the late fusion model, the LSTM has a 2048 dimension hidden state, and the node features are downsampled using self-attention to be of size 2048. The visual and dialogue features are fused through late fusion and pass through a two-layer MLP and softmax, and the output is a prediction over the possible nodes in the environment. In the attention model, the visual and dialogue features are fused instead through top-down, bottom-up attention, and the final layers of the model are also an MLP and softmax. In the attention over history model, there are two separate LSTMs. The former encodes dialogue history, and the latter encodes the current message. Attention via dialogue history is applied over the visual features, and then the encoded current message and visual features are fused through late fusion, followed by an MLP and softmax. We also show a random node selected as a baseline, as well as the center node in the environment. We also show LinuNet skip, which is the state-of-the-art prior work, but on a top-down 2D map. We also test a graph convolutional network architecture over the LED task to see the role that edge information plays in localization prediction. The navigation graph is input to the model, with the node attributes being the visual features and the edge attributes containing the posed transformation between connected nodes. The language encoder is still LSTM, and the GCN architecture learns to model relational information between the nodes of the graph and then outputs a probability distribution over the possible nodes in the environment. Surprisingly, we find that graph networks see only a slight increase in performance on the validation and test splits. While we believe pre-training the GCN models would boost performance, there's not a straightforward large-scale web dataset to pre-train the GCN models on for this task. The final model we propose is the LED-BERT model, which builds upon the cross-modal transformer of VIL-BERT. VIL-BERT is a visuolinguistic transformer model which takes in both visual information and language information and does cross-modal attention between the two. It utilizes a 12-layer BERT-based architecture for both the vision and language streams, with each block having a hidden state of size 762 and 12 attention heads. Our model is constructed of 6 cross-modal attention layers which connect the two modality streams. With this model, we can represent each panoramic RGB node as a series of visual tokens, and we can represent the dialogue as a series of language tokens. Using this input, the LED-BERT model can produce an alignment score between each node and environment and a dialogue. Our localization prediction then becomes the node in the environment with the best alignment. The LED dataset is small, containing only 6K dialogues, and transformers work best with large amounts of data. In order to alleviate bias in training set language and training environments, we propose to extend the VLN-BERT pre-training schema, which uses web-scraped language corpora and other related vision language datasets to pre-train the model in a multi-stage process. In the first pre-training stage, Wikipedia and book corpus are used to train the model from scratch. In the second pre-training stage, we train both streams of the model using the conceptual captions dataset, which contains image and caption pairs. The hope is that the model learns useful language grounding concepts from these static images, which can be transferred to embodied tasks. In the third and last pre-training stage, we train on the Vision Language Navigation Benchmark R2R dataset. This dataset contains path instruction pairs for navigation episodes in the same MP3D environments as the WAI dataset. Lastly, we fine-tune the LED-BERT model on the dialogue localization pairs from the WAI dataset. We evaluate LED-BERT using the same threshold over error accuracy metric, and we compare against the baseline methods. We also include the prior state-of-the-art, LinuNet, and as we can see, LED-BERT outperforms all other methods. In summary, we have proposed a novel format of the environment representation input for an LED model which incorporates more information and leads to higher performance. Secondly, we present a cross-modal transformer-based architecture for the LED task and show after a multi-stage pre-training process on web data, the model achieves state-of-the-art performance. There is still a distinct gap between LED-BERT and human performance, and clear directions include studying approaches to pre-train graph networks for the LED task and experimenting to see the effects of adding dialogue-based pre-training data. Thank you for listening to our talk, and to learn more, please check out our code and visit our project webpage.